Scene script. Have you ever wondered what would happen if you dropped an egg from space? Imagine this. An egg, the common kind you'd find in your fridge, soaring through the cosmic void. The Earth, a massive globe, pulls it in with its gravitational force. Gravity, that invisible force that keeps us grounded, is the first player in this cosmic drama. It tugs at everything, from the smallest speck of dust to the largest galaxy, pulling it towards the center of the Earth. Then there's air resistance, an opposing force that slows down objects as they move through the atmosphere. It's like an invisible cushion of air molecules pushing against the falling object. And let's not forget our star of the show, the egg, a fragile shell encapsulating a liquid center. It's not designed for extreme impacts or the harsh environment of space. So, now that we've set the stage, what do you think would happen to our egg? First, let's consider gravity, the force that pulls objects towards the Earth. This invisible pull is what keeps us grounded and causes free-falling objects to accelerate towards the Earth's center. But here's where it gets interesting. Gravity isn't constant. It weakens as you move further away from the Earth. Imagine our egg, released from space, starting its long plummet. At first, the pull of gravity is weak, but as the egg descends, gravity's pull intensifies, accelerating the egg's descent. However, gravity doesn't act alone. The Earth is not a perfect sphere, and its gravitational pull is not uniform. So, as our egg descends, it could be tugged slightly off course depending on where it was dropped. Even so, the egg's fate is not solely in gravity's hands. Other factors come into play, adding layers of complexity to our egg's journey from space to Earth. Though gravity does its part, it's not the only player in this cosmic egg drop. Enter air resistance, the unsung hero of our plummeting egg. Now let's talk about the role air resistance plays in this thrilling eggscape story. You see, air resistance is a force that opposes the motion of objects moving through the air. Imagine trying to run through a pool of honey. That's a bit like air resistance, but on a much smaller scale. Now, in the vacuum of space where our egg's journey begins, air resistance is virtually non-existent. This means the egg can initially accelerate unhindered, but as the egg descends closer to Earth, it enters denser layers of the atmosphere. Suddenly, it's not free-falling through a vacuum anymore. It's like trying to run through that pool of honey. The denser the atmosphere, the greater the air resistance, and the more it slows the egg's fall. So with gravity pulling the egg down and air resistance slowing its fall, what's left? Finally, we must consider the structure of the egg itself. The egg, a marvel of nature, is a paragon of strength and fragility combined. It's the eggshell's unique architecture that gives it its strength. The eggshell, you see, is not just a simple curve, but an arch, an elegant structure known for its strength. When pressure is applied evenly over the arch of the egg, it can withstand quite a bit. However, the eggshell's strength is also its Achilles heel. Despite the strength provided by its arched shape, the eggshell is incredibly thin, roughly as thin as a few sheets of paper stacked together. This thinness, combined with its fragility, makes it susceptible to cracking under extreme conditions. So to answer our initial question, the egg, despite the pull of gravity and the minimal air resistance in space, would likely not survive the fall due to the fragility of its shell. But isn't it fascinating to imagine the journey it would take?